Welcome to this second session, session A2 of the Python and Research Tutorial 2025. My name is Jamika Marshall, and I am the manager for the Python and Research initiative, as well as Shadow the Scientist. We're so very happy that you've joined us today. A few quick things before we get started. First, if you were in the session yesterday, then you should have received an email from me with the link to the recording of session A1. If you did not receive that, if you weren't here in the session yesterday, just drop me a message to Shadow the Scientist here in the Zoom chat, and I can send you a link. But I will also put the link in the main chat just in case. Also, your messages in the Zoom will come directly to me, and anything that needs to be shared with the group, I will share it out with the entire group so that everyone can see what you're doing. Yes, for security purposes, everyone is muted and your videos are disabled. So please, again, put your comments and questions in the Zoom chat. Now, your questions yesterday, if you were with us, we had some issues with our Slack channel. We have a new Slack channel, and so the link yesterday was to our old one. I will need to add, I will have to manually add everyone's email address to the Slack channel, and then you will get an invite to join the Python and Research PR Slack channel. So once we get started, it'll take me about 10 minutes to add everyone's email address there. Once I finish that, I'll let you know in the chat that everyone has been uploaded and added to the Slack channel. In the meantime, please feel free to put your comments and questions in the chat. All right. Without further ado, we're going to go ahead and get started. First, I'm going to introduce our two awesome mentors for today. And let's begin with Geronimo. Welcome, Geronimo.
Thank you, Jamika. Yes. Okay. So for some people that weren't here yesterday, my name is Jeronimo. I am originally from Colombia, but I'm currently doing my master's in astrophysics in the University of Nice in France. But yeah, and I work usually, or more recently, I've been working a lot with astronomical instrumentation. So doing my research in how we develop and design and get to build the instruments that we can attach to telescopes and learn a lot about stars. And yeah, it's pretty fun, and it involves a lot of programming. So it's exciting to use those skills to also share them with all of you guys right here. So very happy to be here for our second day of the Pyre sessions.
And we are glad to have you with us. Thank you so much, Geronimo. And Parjito, welcome. Oh, where'd he go? Okay. I'm sure
A
you'll.
magic trick.
Oh, yeah, that really was a disappearing
Instantly.
act, to be sure. That was a quick one. I'm sure Parajita will be right back. So while we wait for him, someone has asked for the link to the recording because they weren't here. Let me go ahead and put that in, excuse me, let me go ahead and put that here in the link address. Let me put that here in the chat right now. Okay, so this should be everyone, and this is the recording of the A1 tutorial. Okay. Okay. Now everyone should be able to do that. Everyone should be able to click on that and get to that recording. Now you'll also see in that playlist the recordings for the last maybe 2 or 3 tutorial sessions. So feel free to look at any of those and you'll notice that Geronimo and Aparajito are some of the stars of those tutorials as well. So you'll see familiar faces. Okay. And yes, for the Slack channel, I will add all of you manually. So I have a list of everyone who is currently in the session. Zoom creates a participant list. So if you're here, then I have you in a spreadsheet and I will manually add your names to our Slack channel. And you'll get an invite to join. So, um, so let's see, Aparajito is not
Um,
back. Sure, he will be.
yeah, if
Geronimo,
it's not back yet, I can start continuing where we
please,
left
please
yesterday.
do. Please do.
Sure thing.
Okay.
Let me try and share my screen here, and
Yes. You will
I
say
don't know the exact point where we left yesterday. Let's see if this works.
brilliant.
Um, I hope you can see my screen now.
Yes, we can see your screen.
Wonderful. So I think yesterday we ended up having this. Uh, yeah, we're trying to plot and start analyzing our first color magnitude diagram. And that is a pretty interesting tool that astronomers use a lot. And it was discovered at some point that if you plot, if you remember the info that Maddie shared with us yesterday, there is something that we define as color in astronomy that is not the exact same concept of color that we would use in our day-to-day lives, but it's already very useful. You remember there's each of these photometric bands that astronomers use, so we can be observing a star in the blue, in the green, in the red, and what we define as color is just the difference between those two bands. So for example, in this specific set of images that we're going to be working with, we have some values of the magnitude, which is how bright a star is, in one color that will be usually in this case, minus V. When I think, yeah, bluer. So this side is going to be closer to blue, and this side is going to be closer to red. And we subtract how bright the star is in those two bands, and that's the quantity that we define as color. And that became very important because some astronomers discovered that that quantity is connected to the temperature of a star, and that's a very useful relationship to be aware of, because without touching them, we can understand just from observing a star in two different filters, we can conclude or kind of estimate how hot the star is without even sending a spacecraft to touch it with a microscope and be sure that we know the exact temperature. So that is a very, very powerful tool to have. And they discovered that we can also learn about what stage in their life, in the life of a star, a specific target is, because we can do a plot where the x-axis, so you see here, like we're writing in the x-axis the color, that is like the difference between the two brightnesses. And in the y-axis, we have the one of the two magnitudes. And when we plot it like that, that's what we call a color magnitude diagram. And that's what is usually called a CMD. I already ran some of these cells, so because I was following along with Aparajito yesterday. So I'm not sure exactly on which one we were, but we had like this plotting routine, which I think we have to add the command to show the plots, because an important part. And then we had another function. So these big functions that are pre-written for us, we can leave them as they are because they were written by some colleagues that built these wonderful notebooks for us and help us to this day to really have a very quick and good summary of how we can analyze this data. So some of these functions do some more internal Python work that can be a bit complicated and can be not the point of the activity that we want to do. So in essence, we have one that will generate the plot that we want to see, and we have another one that would write the catalog. So a catalog in astronomy is what we call a big table with targets, which can be, for example, stars. And then we have different parameters associated to each star. So we can be observing a star in different filters. So we want to catalog, in the table how bright the star is in each filter. Maybe we have the information on its distance, on how big it is, on a bunch of things. We can anything that you can measure from a star, you can add it to a catalog. And there's many catalogs out there that have been compiled by many astronomers that have worked very, very hard and since very long ago. So it's very interesting to work with these catalogs, or to plan making new ones, which is what some astronomers still do to this day. When we have new telescopes like the James Webb, like Hubble, that is kind of on its way out, but is still to this day delivering amazing data sets, amazing catalogs. people need to compile and understand what is the relevant information that we can keep from each target that these telescopes observe, and that's how catalogs are set up. So here we're trying to deduce some information about the stars and construct our own catalog. Aparadito is around already. I think I see him here. Maybe he wants to take over if he knows exactly where we were.
Yes, excellent. Thank you.
Wonderful.
Wait, I just saw him. There he is. Welcome back, Aparajito. Very happy to have you with us again.
Okay, I think I hear him. Yes.
Yes, I can hear
Oh,
keyboard.
yeah. Yeah, great. Okay. I couldn't turn my mic on at first.
Yeah.
My internet gave out this time.
No worries. It happens. It happens. We are glad to have you with us again. Geronimo stepped right in and kept us going, and now we'll pass the baton back to you, Aparajito. We're ready.
Thank you so much. Okay, let's see. I will share my screen in a second. Hello, everyone. You probably already know who I am. And I hope Geronimo has caught you up with what was going on in Notebook 3 when we left it yesterday. We covered half of Notebook 3. But, a quick reminder, we were basically trying to make smaller catalogs out of a large catalog. What are catalogs? Well, they're essentially just a collection of data about astronomical objects. In this case, these are stars in the Andromeda galaxy, which is the nearest galaxy to our own galaxy, the Milky Way galaxy. We'll learn a little bit more about Andromeda in the next few astronomy sections today. So let's get back into it. Maddie covered CMDs, color magnetic diagrams, and you learned about the HR diagrams, the Hertzsprung-Russell diagrams, that tell us about the life cycle of the star. All right. So what does a star look like at certain points of its life cycle, all the way from its creation, from its birth to its death that happens, depending on how much mass the star has. And we learned how CMDs or color magnetic diagrams can act as a substitute for that. You should find all of this information in the recording that was sent out recently by Jamika. Check it out, YouTube. And let's jump right back into it. So we went through importing the stuff, all the different libraries we needed. We defined the initialize plot function that creates new figures. And we defined this function called write catalog that essentially makes text files that are similar to the large text file, which is the full catalog. Let's take a look at the data, shall we? Maybe it will clear some things. So this is the file that we're working with, okay? KKHT data txt. So KEK stands for the Keck telescope, the Keck Observatory, located at Hawaii on the Big Island. So it is a ground-based astronomy observatory, and it gives us this data, the velocity and the error in velocity. And we also have the RA and DEC, which are the coordinates. If you remember, they're like the latitude and longitude. We also define something called chi and eta, which is like the relative coordinate, defined in a reference frame centered around the Andromeda galaxy. And then we have the magnitudes into different filters. Now, this data was taken by HST. HST is the Hubble Space Telescope. And we're going to create these 3 files. Sorry. Oh, no, we don't have the files right now. So we're going to create those files. Right now, we have only one, and it's called MS Catalog. Okay. So we're going to create something like this. This is a subset of the full set that you just saw. And please remember that you have to run this notebook number 3, if you want to proceed to notebooks number 5 and 6. Okay, so if you're following along, please make sure you do notebook number 3 first, before you jump into notebooks 5 and 6. You can just watch, that's fine. But if you're doing this with us, with instructors, live, make sure that you do notebook number 3 and you run it in, in roughly the way I'm running it. So this write catalog function essentially makes those little catalogs with smaller subsets of the full catalog. And you can see we have unpacked all the data, the coordinates, the relative coordinates, the magnitudes, velocity, error, and velocity from the text file, KGST data. And we have defined color. Once again, magic of Python NumPy arrays. You can just subtract an array from a different array, and you will get a third array. It will do element-wise subtraction as long as they are the same size. Now, let's create a figure, all right? I added the pld.show. You might have to add it if the plots don't show up for you. Okay, just add it at the very end of the cell where the figure is supposed to appear. All right. So as you can see, this is a scatter of basically all the stars we have in the data set. There are a handful of stars outside these bounds. There are outliers. We don't need to worry about them. For now, these are the stars. These are the 3 groups that we are interested in. And just like the HR diagram, the CMD will also have certain regions for the different kinds of stars. Okay, so you can see a clump here, right? There's a dense clustering of points where my cursor is. I hope you can all see my cursor. And right above that cluster, you can see that there's another less sparse grouping of points, right? You can see that it just kind of abruptly ends. It doesn't, carry on to this region. So this is another group of points. Now, why is this group of points different from the rest? Because you can see that there is a empty channel here, right? That runs in between these 2 groups and this group right here. This is a cluster of points. Okay, this is a third group. So there are 3 different groups of points that clearly appear in the CMD, in the color magnitude diagram. And this is where you see the full power of data visualization in Python, or really any programming language. This is the power of data visualization in science. A picture is worth 1,000 words. A plot is worth many more. Okay, so how do we really mark these regions, and how do we use this plot to actually separate the points into 3 different catalogs? Let's see. So we're going to identify one of the groups as the main sequence, okay, MS. And we're going to define MS as color. Color is obviously the value that runs on the x-axis. But the color is less than 1.75. Color is less than 1.75, so somewhere around here, right? Somewhere around here. So we're talking about this region, right? And we're going to also specify that at the same time, the points should have a magnitude F814W, which, as you can see, is the magnitude on the y-axis in the CMB. That should be less than 23. Now remember, this is an inverted y-axis loop. Okay, so less than 23 means it won't be below 23 in the image, it will be above 23. Okay, so we're picking all the points that are above this horizontal line. Okay, that includes all of these points, but we are saying no, don't include these points. Instead, limit them to here. All right. 1.75 is right around here. So you're going to limit them to the left of that imaginary vertical line. So what does that look like? All right. Let's run that. And can I make another plot? Let's try adding ELD.show right here. Okay, as you can see, we got the same figure, the exact same figure as before, but some of the points have been marked in blue. Okay, and there's a little label here called MS. Now you can see a couple of points right here and there. A few of them are falling outside of those mounts, but that's fine. Okay, we got nearly all of them, right? So we defined MS, and can you guess what kind of array MS will be? Any guesses? It's a Boolean array. Okay, what do we do with a Boolean array? We can use the Boolean array to filter larger arrays. Okay, so if I define something like hope is nothing, okay, let's define. So I'm just going to define a random array. 3, 5, and minus, okay? And you can see that's the array we get. 3, the value of pi, and 0. And now I can index it using a Boolean array of the same size. And just say true, true, and false. So it will pick the first 2 values and it will ignore the third one. Okay, I can change this to false, and I can change this to true, and we'll have 3, 0. Okay, that's how Boolean indexing works in NumPy arrays. And that's exactly what we've done. So what this creates is a Boolean array. You've learned about conditionals. This is combining conditionals and arrays into one thing. Okay, we are advancing. We are learning more advanced stuff. We are combining these simple concepts into something more complex. So we take color, we take the color array and we filter it. We take the magnitude array and we filter it. And we plot the scatter of those points, okay? And then we write the catalog using the filtered versions of all the parameters that we imported from the full catalog, okay? And that's how we get this file, MS catalog, okay? Can we create something similar for the RGB and the AGB instance? So you can see that there's some text here. It says replace A, H, and K with numbers and see what happens. Okay, let's see. Now, does anybody know what this looks like? What this expression looks like? I know the chat is turned off, so this is purely a rhetorical question. But if you took AP mathematics, or if you are in India or China or somewhere where advanced math courses are fairly common in high school, you will recognize this as a parabola. Okay, this is a parabola. This is the equation for a parabola. And obviously, A, H, and K have not been defined yet. So we can define A, H, and K, right? Say ARGB and GB. Now, let's put some random values in. Let's put 1, 2, 5. Oh, it doesn't change anything because I didn't plot anything. Right. So I can move, I can rather copy these lines to here, and RGB starts to plot, and change this to RGB, change the color to something else. And let me refer to something real quick. Okay. Great. So since we're talking about RGB, which stands for the red joint branch, we'll be using the color red, and we'll place our label at, say, right here, because we are marking this region, okay, just for the record. Let's place our label at 5:23 and change the label to RGB. Okay. We have something, but it doesn't look right. So the parabola exists, okay? You can see that the curve goes right down here, and it's covering everything to the left and below. But we want to limit the curve of the parabola, all right? How do we do that? Let's change the value of A to something small, say 0.5. Does that help? It doesn't. What values can we change? Let's turn up the value of K. Let's go 30. Ooh, now we have the opposite problem. Can I go down a little bit? Maybe. That's back. Okay. So maybe the answer is somewhere in the middle. Okay. It kind of looks better than ever before. Now we have to rotate this, right? So how about we change this? Looks like that's making it worse. Maybe something even smaller than 0.5. Okay, this looks almost right. 0.1, and the shape is almost exactly correct. Maybe we need to increase, maybe we need to adjust this one a little bit. No, that doesn't help. Let's go back. Let's increase this one. Scan. Okay, this is almost perfect. Yeah, this works, right? I hope you're all satisfied with this. And as you can see, this marks the RGB stars. Okay, how do we know it's RGB? That's a more elaborate topic. So we're going to kind of skip past that. But just know that if you compare CMDs, you will see that the RGB stars are supposed to appear in this region. So you have the RGB stars here, neatly marked, and the only thing that's left are the stars, and these are, if you haven't guessed already, the AGB stars, the asymptotic giant branch stars. And how are we going to mark them? Well, we're going to remove these RGB tags, and we're going to take advantage of the nature of the parabola by simply flipping it. Okay, it works this way too. Let's write this data to a catalog. It has to be RGB. And we're going to rename this to RGB. As you can see that there is no RGB catalog.txt right now, but we're going to create it. Let's run that. And you can see that RGB catalog.txt has appeared. And does it look correct? It does. Okay, this is a subset of the full catalog, exactly like MS catalog. Now, the final part of obviously is the AGB stars. And like I said, we are going to exploit the fact that we can just flip the parabola, or rather use the same equation to pick the points on the other side of the parabola by changing one sign. And we're going to rename this to AGB. And let's pick the color green because that's the only primary color left, nothing to do with the actual color of the stars. Okay. And you can place it right up here at same as 19.5. Now we have to change this equation, right? To pick the points that are above this curve. And obviously, the way this, these conditionals work makes it so that this one shouldn't change, right? This one says the color should be greater than 1.75, so the color should be greater than 1.75. That's the region of the AGB stars. We cannot flip this sign. We cannot take less than 1.75 for color. So this is the sign that should probably be flipped. And let's run it. Oh, what happened? And let's comment out these lines because they're overplotting the gray points. Okay. I hope this looks good. All right. You can see that the some of the gray points still remain. These were not captured in any of the little groups. But as for the vast majority of stars in the catalog, they have been filed to one of the three catalogs, subcatalogs, new catalogs: MS catalog, HGB catalog, and RGB catalog. Okay. I'm going to make a little tweak here. Okay, yeah, that pushes the line a little bit more. Perfect. So finally, let's get some stats. So the fraction of main sequence stars in the entire catalog is 0.15, 15%, 15.5%. Fraction of stars that are in the RGB sequence are 53%. Sorry. Yeah. And the fraction of AGB stars is 14.9%. And there's a tiny fraction of stars that are not categorized into any of these groups. You can see that it's really small, 16%, which is completely insignificant. So please run node number 3, play around with these values if you want. If you want to get it even tighter, if you think you can do that, please feel free to do that. But I think this looks okay. I think it looks good. Yeah. Any questions about this notebook before we move on to the theory portion of these tutorials?
Yes, we do have a few questions. Let me post them now.
Yes.
Can you go back to line 38? Someone's having trouble with line 38, and I will post these questions here in the chat, in the main chat now.
Sure. Line 38. I think here and mine lines could be different. Our lines could be different.
Maybe if they mean the cell number depends on the times that you've run the
that too depends
notebook,
on
so yeah, maybe they have
how
a
many
different cell
times.
number.
Yeah, so this, for example, is 35 right now. If I run it again, it becomes 37 because the last thing I ran here was 36. If they could be more specific, I can answer their question.
Okay, we have another question here. And also, by the way, I am manually adding all of you to the Slack channel. So I've sent a direct message to each of you. Please check that and drop your email there for me. And I'm manually adding you. You should get an invite, and then you'll be able to post these questions there. And Aparajito or Geronimo will be able to answer for you. But okay, so we have let me just add this from Mohammed, and let me just post this one here.
Okay, I'm opening up Slack. Let's see.
Yes. So the question is, oh, sorry, here's this question again. Let me do it. Oh, gosh. Okay. Oh, yeah. So there's the question, what do these two things mean in the last cell of the third notebook? And I just put a red question here.
Yeah, I'm just getting the slides ready for the next section.
Okay. And while he's doing that, thank you all for your email addresses. They're coming to me now. I'll respond to you directly in a direct message once I have added you.
Okay, what do these two symbols mean? All right. So this thing basically selects the inverse. Okay. And this, okay, by the way, this is a Boolean array. Okay, selected as a Boolean array. And essentially, selected is trying to find a Boolean array that tells you whether or not a star has been selected in any one of the three groups. Okay, so if an element is true in either MS, RGB, or AGB Boolean arrays, any one of those three or two of those three, which is impossible, obviously, or three of those three, which again is obviously impossible. If it is true in any one of those three, then selected will mark that element as true in the new array, which means this is an AND operator. Okay. Wait. It's an AND or God, I got my wires crossed. Geronimo, can you remember?
Oh, I'm sorry, I got super focused replying in the chat. What are you asking me about?
Can you remind me if this is the AND operator or the OR operator?
Yes, I think. Oh, now that you say that, I think it's the OR, but I can check.
Yeah, it's basically the thing where it's if any one of them is true, then the outcome is true. So that's all right. Yeah, that's all. Should be. Close this. Shamika, are there any other questions?
I'm checking now. Just a moment here. I was responding. I'm also responding to lots of people.
Yeah.
Yes. Oh, and Rina has given us a more detailed description of their issue, and I will post that now. And thank you for adding those details. Okay. And just
that is the OR operated, by the way. I'm pretty sure Nico has pointed out in chat that AND is obviously the AND ampersand that we've been using. That is the OR operator.
Excellent. I think that's all we have for right now. And hopefully everyone will be migrating over to posting their things in this panel. But any other questions that are posted here, I will be sure to put them in the main chat, and I'll put that red question mark underneath so you all know to respond.
So the last question in chat along that somebody is getting an error because they did not define the variables. And you have to define the variables or you will get an error. Okay. Now, on to the astronomy section of this tutorial. By the way, Jamika, have we been added to the Slack space?
Yes, you and Geronimo have been added to the space.
I'll be getting an email, right?
Jamika, could you add me on because with my other email that I was using, it's not letting me join, and there's some limitation. I sent you on the DM the other email that I think should work.
You sent me an email with that one?
No, I sent you a DM here.
Okay, will you resend that to me? I'm getting lots of messages, so I did.
Sure. Yes.
I'll look for it. Thank you. Okay, please proceed for our details. Sorry about that.
Yes. Right. So let's talk about something called the Doppler effect. You noticed that we had the data for the velocity of these stars. Okay. Now, what kind of velocity are we talking about? Because everything is relative in space, right? If you're going to measure the velocity, how do you measure the velocity? In which direction do you measure the velocity? What is your reference frame, right? These are the questions you have to ask because there's no up and down, there's no standard frame in space with respect to which you can define velocities. There are frames of reference, there are, some standards, but you have to define the standard that you're using. So it's not like measuring the velocity of a car on Earth, where it's obvious that you're measuring the velocity with respect to the ground that it's traveling on, right? When it comes to space, usually or often we are measuring the velocity with respect to the Earth or the Sun. When you're within the galaxy, these values can vary quite a lot. The geocentric velocity, the Earth-centric velocity, and the heliocentric velocity, which is the sun-centric velocity. These two measures can vary because the Earth is moving around the sun, and that adds a difference, right? Now, when it comes to other galaxies, this difference is very small. It's almost negligible, but we use the standard of the heliocentric frame, the sun-centered frame. Okay, so how are we doing on time? Okay, I should speed things up a little bit. Now, the Doppler effect is what helps us measure the velocity in our line of sight, okay, along our line of sight. So this is called the radial velocity, okay? It's called the radial velocity in astronomy because it's radially outward or inward, okay? It is in the direction of your sight. It goes straight towards you, or it's coming straight, or it's going away from you, okay? These are the two velocities. These are the two kinds of velocities that you can measure using the Doppler effect. What is the Doppler effect? You're very familiar with this in terms of sound. It occurs with anything that travels in waves, including sound and light. Have you ever heard an ambulance or a police car go by, right? Go by your house, or, when you're standing by the street. It goes by very fast, right? If there's an emergency. And obviously the sound gets louder and louder as it approaches, and then it gets quieter and quieter as it goes away, as it moves away from you. But that's not the only change in sound that you will notice. You will also notice that the pitch of the sound changes. The pitch of the sound increases, right, if it is approaching you, and it diminishes, it decreases as it's receding, okay, as it's going away. So if you carefully hear a siren, aside from the change in volume, there's a change in pitch as an ambulance is moving towards and then moving past and away from you, okay? So that is the Doppler effect. You can see that there's an observer here, and basically the sound waves gets bunched up, right, as they're traveling. As the ambulance is traveling, it will send out one sound wave, and then it will have moved towards the sound wave by the time it emits a second sound wave. So the sound waves kind of get bunched up, and that's how we can imagine it in terms of sound. For light, there's a couple of ways to imagine it for light. And when an ambulance is moving away, it releases a sound wave, and then by the time it releases the other sound wave, it has moved away from the previous position where it emitted the previous sound wave. So the sound waves kind of get spaced out, right? So that's how the change in pitch happens. Something very similar happens with light. When a source is moving towards you, okay, the frequency of the light increases, the wavelength decreases, and when the source is moving away from you, the frequency of the light goes down and the wavelength increases, okay? As you know, the speed of light in a medium is always constant. So when frequency goes up, the wavelength goes down. And when frequency goes down, the wavelength goes up, okay? So when the light source is moving towards you, the light looks bluer than it's supposed to. And when the light is moving away from you, the light looks redder than it's supposed to. Okay? What do I mean by this? We'll see. Now, there are we casually call Doppler shift redshift in astronomy. Unfortunately, that's a little bit of a confusing term because you have to define what kind of redshift you are talking about. There are three kinds of redshifts in astronomy that we colloquially refer to as redshift. So one is the type that occurs from the motion of galaxies relative to other galaxies. All right. So we are in a galaxy of our own, the Milky Way galaxy. We can look at other galaxies, the light coming from other galaxies, and we'll see that the light is either redshifted, which is the case for the vast majority of the galaxies, or it's blue shifted, which is the case for some exceptional galaxies. Now, the fact that the vast majority of the galaxies are moving are redshifted means that the vast majority of galaxies are moving away from us, okay? And that's why that redshift is actually not caused by this, it's caused by this, okay? It's type 2. It's because of the expansion of space between two stationary objects. But sometimes you see an anomaly when, you will see a galaxy that's blue shifted, and then it occurs from the motion of galaxies relative to other galaxies. Okay, so galaxies in one group kind of moving away from or towards each other, orbiting each other, that sort of thing. But as a whole, the universe is expanding, so that gives us type 2, another kind of redshift. And finally, there's gravitational redshift, which happens when light passes near a very, very heavy object like a massive black hole, or even massive galaxies. The sheer mass, the gravitational force kind of bends light and slows it down. So that causes redshift. So there are three kinds of redshift. We will concern ourselves with type 1, which is the relative motion of galaxies. We are not concerned with the expanding universe right now. We're not concerned with, massive gravitational potentials. Now, what can redshift help us do? It can help us measure the distance of deep space objects. So like I said, most galaxies are moving away from us because of the expansion of space-time. If you know how fast space is expanding, space-time is expanding, you can look at a distant galaxy, measure its speed, the speed that is moving away, and you know exactly how far it is, because the further something is, the further it is moving away. Okay, that's just how space-time expands. So it helps us measure the distance of these space objects. Determine the relative age of galaxies. You can, if you know how far away a galaxy is, you can basically know how long ago the light was emitted, and that helps us, know the relative age of the different galaxies. And finally, it can help us find exoplanets, which are planets that orbit stars other than the sun. Basically, when a planet orbits a star, it tugs on the star. Okay, think of it like ballroom dancers. Two people dancing with each other, and two people are kind of moving towards a common center. Okay, moving around the common center. Now, if one of the partners is larger, then they will move less. They tend to move less. And they can spin around the lighter partner, the smaller partner, and you will see much more movement from the smaller partner. That's kind of like the planet. And the larger partner is kind of like the star. Okay? So if you can still notice how the larger partner is moving, you will be able to guess where the smaller partner is. Yes, Shamika.
Okay, quick question. And I posted it in the chat. In the type 1 redshift that you mentioned, if they were redshifted and they're moving further in the blue shift, which are exceptional, is it possible that our galaxy is moving towards that point, making it appear blue?
Right, if the shifted area moving further and blue shift.
Oh, you got it. Okay.
Yeah, that is what it implies. If a galaxy is blue shifted, it implies that that galaxy and our galaxy is moving, they're moving towards each other, okay? They're moving towards each other, it's relative. That's what it means, yes. You're correct, that is the correct case. So finding exoplanets, you can look at how the star is moving, okay? And you can use that to predict that there is an exoplanet there. Because stars don't just wobble on their own, right? There must be something. If you see a star wobbling, there must be something moving around it. How are you going to measure, though, that a star is wobbling? That's very, very tiny movement, on a cosmological scale. How are we going to measure that? How are we going to make that precise? Redshift. You can use redshift to make incredibly precise measurements of velocity and changes in velocity. So if the movement happens along the line of sight, so that is unless the planet is orbiting, literally flat, perpendicular to our line of sight, you can measure that change in radial velocity, and this is in fact how the vast majority of exoplanets till date have been discovered. This method reigns supreme. There are more, there are newer methods like the transit method, but radial velocity has yielded more results than any other method till date. Okay, so what does Doppler shift look like on a spectrum? So if you take the light of a star and you split it into a rainbow, that's called a spectrum. Okay, the sun spectrum is called a rainbow. A rainbow is nothing but nature taking the spectrum of the sun's light. Okay, we can do the same for the light of other stars. We can do it artificially using our telescopes. Now, once you have taken that, yes, Shamika.
Oh, please finish your thought, then we have a question.
Oh, yeah. Okay, so once we have taken the spectrum, you will notice that there will be some dark lines within the spectrum, okay? And these lines basically occur because the stars have certain elements and compounds on its surface, okay? And the light passes through that atmosphere of the star. Some of that light is absorbed at very specific wavelengths, and that is always unique to the substance present in the atmosphere. And if you identify the substance from these patterns of dark lines, we will also know at exactly which wavelengths these lines are supposed to show up. Okay, and when they don't show up at those wavelengths, we will know the difference. And that is how we measure the redshift. Stationary, this is how the spectrum is supposed to look like. Okay, but when it's redshifted, the dark lines will be shifted to the right, to higher wavelengths. That is the redshift. And this is exactly what you see in spectrum. Jamika.
Okay, thank you. Yes. The question here is, okay, how do you account for the temperature of stars if they're in constant relative motion?
So the temperature is calculated from the overall shape of the spectrum, essentially, which we can see in this next slide, I believe, here. So this doesn't mean anything to you right away. This is the entire spectrum of a star. or rather most of them. Okay, and the shape of the spectrum gives you essentially, or rather where it peaks, essentially tells you what the temperature of the star is. You can look up black body radiation if you really want to dig into the physics. But obviously, as you can guess, redshift might play a role in obfuscating this information. So let's see how we can fix that. So right now, this spectrum, it doesn't mean anything to you, right? You can see that there's a rough curve, some squiggly lines, and there are huge dips, okay? These dips, you can actually match them to specific wavelengths, okay? And the black line, the black spectrum is what you see. But if you track the dips, they match up to elements, and you will know that this spectrum has a Doppler shift, right? And you could adjust that Doppler shift precisely after that once you have identified the exact elements, because you know where they should be instead of where they are. You can move them to where they should be, and you'll get the rest frame spectrum of the star. Then you can measure the exact temperature of the star. Okay? That is how we measure the temperature of the star. Shamika.
Yes, thank you. This is a follow-up to that previous question. How are the ages for the stars determined?
Oh, that is
a spicy question.
yeah, that is a longer question. Essentially, we try to figure out where it lies on the HR diagram. You can kind of predict from the temperature, the mass, the luminosity, stuff like that. And still there are some unknowns. Stellar modeling is a thriving field of astronomy. We try to create more and more precise models for more and more for very specific categories of stars, because there are so many different kinds of stars. Depending on the composition, a lot can vary really, especially if it's a binary system and one star is cannibalizing the other. That's another, that's much harder to predict. You're adding so many more variables. So that's a let's just say that's what a few classes of astronomy, at least what you asked there. But I think I covered the basics. You can basically place a star somewhere on the HR diagram using the parameters that you observe, and that gives you a clue about how old it is. Geronimo, am I correct?
Yes, I mean, I would agree with you. It's also my understanding. I was just typing a little reply
Yeah. Go
to
ahead, go
Barbu.
ahead.
But I think I understand age determination is one of the biggest challenges, because usually you determine the age of a star using those kind of hints that you can get from where it is in the HR diagram, from comparing it to the models, as Parajita was saying. But you always get like a big uncertainty on that. Like you have a big error bar to the value of the age of your star. So you really need a lot of observations. You need to compare the observations with simulating in computers how the physics of stars makes them look like if they're from a specific mass and of a specific age. So you kind of have to match all of that and put kind of the two pictures in front of you and see how close it looks. But I've seen some people work on that, and sometimes it feels like they're kind of guessing a little bit from the pieces that they can gather from observing the star. But it is definitely a very interesting problem that the guys doing stellar astrophysics do work a lot about. But it is very cool.
Yeah, exactly. That there are quite a few unknowns. But good question. Good question. Okay. Now let's break this down into a mathematical formula. As you can see, sorry, I think I mixed up the blue and black lines. So the cyan lines they're the red shifted, they're the Doppler shifted wavelengths, and the black lines are the red shifted, the rest frame wavelengths, rest frame spectrum. So taking these wavelengths, taking these two kinds of wavelengths, lambda nu, which is the Doppler shifted wavelength, and lambda rest, which is the rest frame wavelength. Sorry, this doesn't show up correctly because there's a dark mode thing on my browser, but this says 1 plus v over c. You can barely see it. Let me see if I can fix that. Yeah. So 1 plus v over c, that is the formula. 1 plus v over c times lambda rest equals lambda nu, okay? Where v is the velocity of the source, in our case is the velocity of the star, and it is negative, it is moving towards us, and it is positive, it is moving away. And c is obviously the speed of light in a vacuum in our case. And that's about it. That's Doppler shift.
Brilliant.
So
Thank
weird.
you.
Yeah.
The link to these slides were pasted a long time ago in the chat. You may have to scroll to find it, but I will paste them back. I'll paste the link back here in the chat once I finish sending everyone an invite to the Slack channel. And by the way, as I see some people are starting to get into the Slack channel, if it's asking you to upgrade your account, don't feel the need to do that. There is a trial pro account if you want to do that just to get into the Slack for this session. Please feel free to do that. Otherwise, you can keep posting your questions and comments here in the Zoom chat, and I will make sure that they are posted in the main chat, and I will share them with Aparajito and Geronimo. All right. Aparajito, thank you. Geronimo is up next.
Okay, we're ready. So now we're gonna have a look at notebook 4. Before that, I was leaving a little comment on the question about the age, saying kind of summarizing what I was discussing with Apardito. I also remember there's a very cool method that is like if you have observations on more than one star, but you have like a family of stars, like a group of stars that you know that were born kind of at the same time within the galaxy, that really helps because you can do an HR diagram of that stellar population. So using stellar populations to compare with, again, with the models, with the simulations, is usually the way you go to really have the more accurate estimates that we have nowadays. So that is very cool. I still think I don't work on that, but I have some colleagues that work with that, and I think they kind of do magic to really squeeze the information from the little bits and pieces that we can observe from so far away from stars. That never stops amazing me, I think. But back to our data set. So we're working with as Aparajito was mentioning before, we're working with the data set from the Andromeda galaxy. And now we're gonna inspect some interesting effect that is gonna connect with Aparajito, with what Aparajito just told us, and it's the radial velocity that we can infer from the Doppler effect, and this will be evident when we start plotting all those stars that we can that we have observed from the Andromeda galaxy. That fun fact, I mean, it's approaching us, but now through observing the data, we will see that come up. We will understand how it is measured, that people know, okay, that is a huge galaxy that is approaching our galaxy at very high speeds, but is so far away that that's going to take millions of years to happen. So yeah, I think we're going to start first with the notebook, yes, and then we're going to have another short conversation on the astrophysical context. So let's do that. So remember this activity. We start by when we have a new notebook. Oh, I wanted to do also a quick comment on something that some people are getting confused in the chat, and is that it's not maybe completely clear how to navigate the files when you have Jupyter Notebook. So in this case, for example, when you just run Jupyter Notebook, remember that you have this home tab that opens here, and it usually opens in your home directory. So you can see that I have a bunch of folders that are within my computer. So it's like this all are folders that I have created. This is Windows, but like I have created these folders within my local files. Uh, and I have downloaded and saved the notebooks that we're using in some specific route. So in this case, for example, I saved them in the documents folder. So I can just open Jupyter, go to documents, and then I'll find the SIP Python workshop folder. And this is where I should find the folders that I have downloaded, or like the files that we're working with today. And here in programs is where we have everything. Since I've been working on solving them, you'll see that I have a solved copy that I've been using to run to check that everything is smooth. But then I have the blank copy that's the one that you should have, and maybe you're working on right now. So yeah, this is the one that we're working on. So if you're not working on an installed version of Jupyter, and you're maybe working on an online version of Jupyter, you might have to use this button that's right here that says upload. So you can use that. That was a tip that Nico was telling us earlier through the DMs. So yeah, that's also useful to upload them there, but make sure that then maybe you can if you're working online, that you can save it and then make sure to download it again. So you can, I think I can still do it in this local version. You can do file and you can do download, and that will download this .ipymb file that you can then use again on Jupyter, either online or offline. So that's an important comment that I wanted to make, just to make sure that everybody has their Jupyter navigation working. Okay, so we start first by importing our libraries, NumPy, to handle the lists of numbers that we're going to call within NumPy. Those objects are the arrays. And for plotting, for displaying beautiful information, we use matplotlib. So anytime, remember, you see np dot something, that is a function that is proper of NumPy. You see plt dot something, you're going to have a function that is proper of matplotlib, that is for plotting, visualizing, and stuff like that. So we have the spectra that we saved from no, we say we have some spectra that has been observed from a telescope somewhere, and we can use or we can access the information from those stars that have these beautiful names that are like telephone numbers, because when you have so many stars in the sky, you can just give a name to each of them, like a simple, easy to remember name, because there's so many of them that it's easier to just assign a unique code to each of them. So that's what many catalogs do. They will have like a specific number. So here we're gonna have in the home folder, if you go back to the data folder in the SIP Python workshop directory, you'll see that we have these three that have the underscore spec suffix to them, like in the name of the file. Those are data sets that if you open them, you in Jupyter you can open any of these text files, and it should show you something. Maybe it's really heavy, but okay, there's something. So it's like you have two columns that will allow you to draw a spectrum as a column that has wavelength values, and another column that has like flux values, flux, intensity, magnitude. These are words that usually refer to how bright a thing looks. So a spectrum is nothing more, as Aparajito was explaining earlier, than how bright something is in each different wavelength, right? So that's good to keep in mind. So we have three of these files that will work the same. And what we do in our notebook is that we're going to call that information into our code, and we're going to plot it and try to compare it with what we would expect those stars to look like when you see their spectrum. So that might be kind of weird to think about at the beginning, but a lot of it is already coded for us here. But the first step that we have to do is that we have this function that allows us to apply the model of the Doppler effect. So if we do a Doppler shift, if we have some rest wavelength that we have written here as rest lambda, and we want to displace it to a different wavelength through the movement of the source that is moving to a specific relative velocity to us, as the effect that Aparajit was showing to us. We have to complete this relationship right here. The new wavelength is not exactly the same as the old rest wavelength. We have to adjust it by some specific factor. I think I have the slides open here so we can see it here. Yes. So we see that it's like we multiply the rest wavelength by 1 plus v, which is the velocity of the star in this case, of the source that we're observing, divided by c, which is the speed of light. So what I'm going to do is that I'm going to just add those quantities right here. So I'm going to use c, so I can define that variable here. And it's 300,000 kilometers per square second, not per square, per second. It's not an acceleration, it's a velocity. So we can do that either by writing 300,000, right? And I'll add here a little comment that reminds me that that's kilometers per second. But also we could use the scientific notation here, which is written as 3 times 10 to the 5. That's how we write it. So that's a useful compact way of writing it, but it will work either way. So we can keep 300,000, we can keep 3e5. It's a matter of preference. And then what we do is that we have that before the rest wavelength, we have to multiply that by this factor that is 1 plus v over c. I have defined c, it's an internal variable of the function, so that's not going to give me any problems. And rest lambda and v, I don't have to define within the function because they are the arguments of the function. So whenever I call this function, I have to give those two values, and then the function is going to do the computation internally and simply give me back or return the new wavelength. So let's make sure that this makes sense. If we say this velocity can be positive or negative, as Aparajit was telling us. So if it's positive, it's some source, some star that is moving away from us. And then if it's negative, it's something is moving closer to us. So notice that if the velocity is positive, this will be a number larger than 1, which will result in the new lambda to be increased with respect to the rest lambda. If it's the opposite case, if v is negative, then we have that this quantity is a number smaller than 1. So that's going to decrease when we multiply it by the rest lambda. That's going to decrease it. So we have to make sure that we see that makes sense. Because when we do that, what's going to happen with a star that has some rest reference wavelength value, some lines that we can see in its spectra that we can measure very accurately. What's going to happen is when it moves away from us, we're going to see that that whole spectrum shifting towards the longer wavelengths. Because if this is positive, then the wavelength that we will observe, the new one, is going to be longer. It's going to be larger. The opposite case is when the velocity will be negative. When the star approaches us, then the whole spectrum is going to move towards the shorter wavelengths. So we can just have a sanity check when we read the equation that we just wrote, and then we can just execute that cell, and we can make sure we can start doing tests with it. So let's have like a rest value of reference. This is the H alpha line, so it's one of the lines that are characteristic of hydrogen. So we have that line, if we observe some hydrogen in the lab, happens at 6,563 angstrom. So we can put here the angstrom comment to know that we are using that unit. And what we can do is that we can call our function. So I'm going to just copy the name of the function and paste it here. But what we do is that instead of rest lambda, we can simply write the name of the one that we just defined. So it would be rest h alpha. And then in velocity, we can pick different values. The comment here suggests us to try maybe 200. So let's try 200 and see what happens. When we run this, it will define rest h alpha as this value, and then it will call the function and use that wavelength and run it for the velocity that we're telling it to do. So it's 200 in this case. And you can see that it's positive velocity. So what we get is a slightly larger number here. So it's like it was 6,563. Now it increased slightly into 67. We can do that again. I'm going to click this plus button right here to add another cell down here. And we can call it again to compare with what happens when we put minus 200. So if we run that, then you see that it started at 6563 and now it's going down to 6558. So it's decreasing a little bit. So depending on the sign of this, it's going to be an increase or a decrease. And depending on how big it is, you can get crazy numbers. For example, if I put 2000, see that it's going to decrease even more. If I put 20,000, and you can go to redshifts or like velocities that are very, very high, and that generates redshifts or blue shifts in this case that can be very high, that can be very, very noticeable. But let's keep it on the case that they are asking us. So 200 minus 200. And now we can use this function and use the data that we have been given to compute some stuff and like to plot some spectra comparing with what we would expect from the theory. So here we have these three names. We can pick one of them. Let's, I don't know, say pick the last one, 49, 14, 22. And we're going to replace the string variable that says star name goes here. You're just going to replace that. Make sure to keep the quotes because that's what tells Python that that is a word. That's not a number. That's not the number 49, 14, 22. That is just the tag. It's a name. You know, it's like if I wrote Geronimo, I would have to write it in quotes because that's a name. It's a set of letters, of symbols that I use to identify the file. And the file will not be read as a number. It will be read as a title of a file. So then we can, what we're going to do here is that we have these stars and they might fit with one of these three types that Aparjit was mentioning to us. So they can be either main sequence, red giant branch, or asymptotic giant branch. And each of those types are different families of stars because they can have different spectral features. So that's where we're gonna look at now. We have some reference spectra that we can compare the spectra that we're seeing here, that we're gonna see from, that we captured from the star, with the ones that we would expect. So we just replace these two. These other lines of code are just to help us locate the right files in the right folders, but you don't have to worry too much about them. So we run that, and then we can then run this one, make sure again, remember that some of these lines, some of these cells will lack the plt.show line. So I'm adding it here because we're plotting something. Notice that we say that we're plotting. So if we're plotting something, make sure to check that you have the plt.show command. And when we run that, we're running, we're plotting the spectrum of this star, the star with this name, and we're comparing it to the spectrum that we have already stored, that we are given, of a main sequence star. It's not going to match completely if they're the same type, but it's going to be very, very different if 4, 9, 14, 22 is not a main sequence star. So let's plot that and see what happens. And notice that this is clearly not the right type of spectrum that we want to compare our science target in this case with, because we're comparing it with a template main sequence star that is going to have this shape. So it's like a hill that starts kind of high here, in this case with around 6,500, 6,700. It has this peak, but then it falls pretty smoothly. Here we have a more flat surface with some specific bumps somewhere, but it's really not following the same shape. So that's going to hint us that, okay, the right template that we want to compare the science target with is not a main sequence star. That's hinting to us that 49, 14, 22 is not a main sequence star. So we can change the template by simply, instead of MS, we can write RGB. and you can run that cell again. Make sure to run it before you run the second one, because that's going to change, that's going to update the value that we just changed. Um, and then when we run them, oh wow, look, it looks pretty good. It looks like it really, really matches the shape of our spectrum. So that is a hint that maybe the science target that we're studying right now, 49, 1422, probably is an RGB star. Let's run just to check the AGB one. So if we run that, look, it deviates more. So that tells us, okay, the closest one seems to be the RGB one. So that hints to us that the target that we're interested in seems to be an RGB star. You can do the same, and please try to run it at home, maybe later tonight, maybe on a different day that you're going over the notebooks again. Play around with the different stars. Check if this one also is an RGB or is an AGB, which of them are main sequence. You can try to check that and compare with all of them. And remember that you can always take screenshots of the images. There's a command that allows you to save the plots, but sometimes it's quick to just take a quick screenshot and save it, and you can put it in a single document and look at them side by side and compare them. But yeah, whatever. The point is, let's have RGB, and then we see that this kind of matches, but now we match the type of spectrum that we're seeing, but we not necessarily are in the rest frame wavelengths of the spectrum. You know, maybe our star, which is very likely because if this is a star in the Andromeda galaxy, for example, um, this is clearly moving with respect to us. There's some relative velocity going on. So the lines and the main lines that are going to guide us are like these little valleys, these absorption lines, we call them. Uh, we're going to use those lines to maybe follow and try to line it up properly by changing the velocity. So remember, if we put the velocity on the negative range, we're going to effectively like pull the spectrum, the red one, towards the left because it's going to move it towards the shorter wavelengths. And then if that's what we will call blue shift the spectrum. And then if we do the opposite, if we put a positive velocity here, so in our guess that we're gonna put it in this little variable that we define here, and then we shift the wavelengths. What we're gonna have effectively is red shifting it if we put a positive number. So depending on the sign that you put here, you can notice if the spectrum moves to the right or to the left, and you can decide if what you're doing is working correctly. We can even zoom. We can zoom in closer to what we want by adding the command. I think they give us the hint right here. So you have this command set x lim, so that allows us to plot everything, but then we just tell, okay, but just show me the x values range that go from 7,000, so right here, to 7,200. So that's going to be like a more narrow spot here that is going to allow us to align properly the spectra with these little bumps that we have down here. So we can run that. We can do x set xlim, and this one has two parentheses, and we write 7,000 to 7,200. When we run that, we have a more zoomed in little spectrum, and we can start to play around. I think I remember you have to play around with this and you'll find a bunch of different values, but I remember that like negative 200 should kind of do the trick. And remember that this should not fit perfectly because we're comparing our science star, which is a real star that has been observed with a spectrograph, with some template spectrum of a star. So it's like we assume that it's going to look similarly, so the valleys might match up kind of nicely, but it's not necessarily going to be the same. So you can start playing around with this. So let's change from 200 to 250. Let's see what happens. And you see that some of these little bumps move around, and you can see and play around and try to find a good fit. When you do this kind of like methods that are more just look and like click and play, you kind of just like try to see it by eye. There's not a perfect solution for it. You can only approach it as much as possible, and then when you're satisfied, you can just leave it there. So that's kind of the plan. So you can do something like this and try to match up the two spectra like that. So yeah, You can try to do that with the different stars, and then if you want, you can take note of the values that you found. So, for example, if you want to do that in this cell that has some text, you can go and check. Okay, I wrote negative 250, and this is for the last star, 49, 14, 42. So I can put here that I put negative 250, and the template is an RGB. And then when you're done editing the text, you can do Shift Enter, and that's gonna save the text on this cell. This cell, you'll notice like the cells that have text say Markdown in the type of cell, and the ones that have code, they say code. So you can easily switch the type of cell that you're working with if you want to just write things, write nice headings like this one. You can play around with the type of cell that you have, so you can interchange code with text, and you can make a more readable notebook. But yeah, feel free to play around with the different templates and the different spectra on your own time. No rush. And if you need any help, you can ask us on the Slack, and we're gonna discuss a little bit more about the results that you're getting over there. So that could be fun. And then what we can do with it now, this was only one start that we were like considering. Okay, let's look at the spectrum and all. But what, like if we have thousands, hundreds of thousands, maybe even millions of stars in our catalog, we can just open the full catalog and do a velocity map. Like we can measure, if we have like an algorithm that can do this checking and between the reference spectra and with the actual spectra that we have, and measure the actual velocities of each of the stars. We can do a radial velocity map. So it's like we can do a map where each star of the whole galaxy has a specific value of velocity, and that's going to tell us, oh wow, this whole galaxy that is composed of a ton of stars is gonna be turning in a specific way, or is going to moving in a specific way. So by observing the movements of the pieces, we can tell what's the complete movement of the whole, of the whole galaxy in this case. So that's pretty interesting. We start by importing the catalog. This has a bunch of different parameters that we're working with. Mostly at the beginning, we have the coordinates. So RA and DC, RA, DEC, are the sky coordinates that we see when we point a telescope towards the stars. So that's going to simply be what point of the sky the telescope that took these images was observing towards, or was centered in when it observed that specific star. And then within the data set of Andromeda, we can define two specific coordinates, two specific angles that allow us to know with respect to the center of Andromeda, how far off we are. And you're going to see that soon, because we're going to use those psi and eta coordinates to plot the disk of Andromeda. Then I think we have two brightnesses, like two photometric bands. So the magnitudes, or I think the fluxes in two photometric bands, and that's going to be helpful to plot some of the brightnesses and values. If we want to do a CMD, like a color magnitude diagram, we could do it with that. So it's pretty helpful. And then we have the array of all the velocities, and it even gives us the error in the velocities, which is very important when you want to present scientific results. You present them, as I was telling earlier with the example of the age measurements. You want to present your age value, and you want to say, okay, but I'm sure that's the value within some range, like maybe it's plus or minus a certain number. So in this case, these scientists are very organized, and they measured a specific velocity, but they also specify how accurate that velocity measurement is. So we can simply run this, and then we have some conversion factors that are going to be useful for the functions that they have already defined. We can run that. And here, let me check that. I think this should have a plt.show here. If you're running it alongside us, make sure that you have that. Make sure that you put the plt.show, and you should have this weird looking shape, like this disk that is like formed from all the stars that have been observed from the galactic disk of Andromeda in this survey, in this specific catalog. And you see that this color bar is showing us the values, or it's kind of showing us kind of a hint of the distribution of values of the radial velocity. So the ones that are bluer in this case are going to be more negative, but then you have some more greenish, yellowish ones that are on top that are going to be up to 100. So that's important to keep in mind. And there's something very interesting that we can play around with, because we can change the way that this is color coded to make it more intuitive. The thing is, that we can do what the notebook is telling us to do, before we can label, or like be sure to know which part of the galaxy is actually blue shifted, which is red shifted, which is none. Uh, and we can first, like, let's run this again. Let's make sure to have the plt.show for that to work. That's the same plot, and we can change the coloring style. You can go to this website that is showing here. This is the manual of matplotlib, and it's showing all the possible color maps that you can use. I think if we use here seismic is one that we have used several times, uh, to do this kind of visualizations. You'll see that it becomes red and blue. That's kind of the scale that we're aiming for, because we're gonna go to discuss this, or like we want to interpret this as what part of the galaxy is getting red shifted and what part is getting blue shifted. So you see that blue is going towards the negatives and red is going towards the positives. So that kind of starts to go in the direction we want it to be. The issue is that this is kind of misleading, because it would tell us like, okay, all of this side is red shifted, all of this side over here is blue shifted. But the issue is that look at the zero in color, like what we would expect to be neither blue or red, the white part. We would like that to be in zero. Like that doesn't make that much sense that zero is so far within the red already. So what we can do is that we can use symmetrical boundaries in the color bar. So we can go all the way from minus 700 all the way to 700, and in that way we achieve to put zero in the middle, and that's going to match up kind of nicely with the white in this one. So let's put 700 instead of 100 in the Vmax. So you see that the color bar that we're plotting has these two parameters that we can change. You can play around even with this if you want. Put in crazy numbers and see what happens. You can also change the color map that it uses, but the bar will follow one extreme of the color map that you choose in the negative side, and the other end in the positive side, and you can play around with those two uh, parameters a lot to see when you're satisfied with the way you're visualizing the data. So let's run it. Now I put the minus 700 as the minimum, and it will go all the way up to 700 instead of 100 as we had it here. So let's run that. And here we go. Oh, wait, no, it's not this one. It's this one. Yes. So now you see that actually most of it seems to be kind of blue shifted in this sample that we observed. It has some area of it that is starting to go into the white. So what we see is that most of this section of the Andromeda galaxy that has been observed here is kind of moving towards us. Like this is the end that is moving towards us, but not at the same rate. Notice that this side here is way bluer. So that means that that part is kind of rotating more towards us, and in like a faster with a faster speed. So that's kind of the interesting result that we can get from this. If we get huge maps of a bunch of stars in a galaxy, I don't know, for example, in the Magellanic Clouds, which are dwarf galaxies that orbit the Milky Way, you can pretty much determine a lot of their kinematics, a lot of the ways that they are moving, and that leads us to a new topic that is galaxy kinematics. We can now, this opens the door through spectroscopy. We open the door to understanding how galaxies interact and move, and we can actively, even if we take a picture of them and it looks like a frozen snapshot, we can take a closer look, and we can find that actually that snapshot is very much in movement. It's like in motion actively as we are looking at it. It's just that it's such huge distances that we cannot witness the motion with our own eyes, or like just by the snapshots we take with a telescope. We need to use the accuracy of spectroscopy to really get the scale of the velocities that this is moving as, because In this case, you see that the scale is going all the way, as we define it, all the way down to 700 kilometers per second. That is very quickly. Uh, the size of a city is a few tens of kilometers. Imagine if you can go from one state, for example, in the US, from one state to the next in a couple of seconds. If you can go from, I don't know, you can cross, in my case, I'm living in France. If you can cross the whole of France in just 1 or 2 seconds, that's kind of the speed at which these stars are moving with respect to our point of view. So that is a very interesting way to put it into perspective that we should still keep in mind. And I think that reaches the end of this notebook. Here's an interesting question. You can think about it also later, and we can discuss it on the Slack. What is the systemic velocity, or like that would be the average velocity of Andromeda relative to us? So you can see this chunk of the galaxy, and you can think, okay, maybe the whole galaxy is moving towards us. Where is the side that is kind of more average, like that? That's kind of the velocity of the center of the galaxy. So that's pretty interesting. That is a cool question to have. You can already have a hint, maybe, that I would guess is somewhere in this area, like around the negative 200, maybe a little bit less, if you think of the average color of this plot. But yeah, but that's very interesting. But this galaxy is effectively rotating while moving towards us. And that's a very cool result that we get from spectroscopy. So that's on that. Next, we should move, sorry, Jamika, to the next presentation, right?
Yes, absolutely. You are correct. Thank you. And let me
Wonderful.
just say, for those of you who are, I see you're joining the new Slack channel. Awesome. Again, if you are having any issues, if it's asking you to upgrade to pro account, don't do that. You can just continue posting your questions here in the Zoom and the Zoom chat, and I will make sure to post them in the main chat and also just raise my hand and share them and bring it to the attention of Parjito and Geronimo. And we now have Raja has joined us here as well.
Wonderful.
We have 3 people who can answer your questions. All right.
Very glad.
Please proceed, Geronimo.
Cool, cool. Okay, so we can start by looking at a couple of really nice animation. Let's see if it works if I open it in the presentation mode and if it lets me click on things and maybe let them play. Yes, beautiful. So this is a wonderful landscape view that you will have if you go to some of the more clean and pristine skies that we have available on Earth. You will see this kind of whitish disk floating over your head. It's not going to be moving at this speed. This is pretty much like a bunch of images played in sequence that have been taken across one whole night. And you can see, then you can accelerate that and definitely see the motion of the galactic plane of the Milky Way across the sky. That is a beautiful sight that as a humanity we should cherish and we should really, really protect, because all forms of pollution that we are dealing with nowadays can leave us without the possibility to see this from anywhere in the world. So we really need to protect our skies, and it's very important that we can see this still, and our following generations can keep looking up to the skies and having these beautiful sights. So I just wanted to share that. So we have this view, and that connects with what we're saying. In the sense that this is the view that we have from our galaxy. So this is the galactic plane of the Milky Way. It's like we are seeing our city from within it. Oh, I love this. Come on, Raja, please.
Just a
Feel free
couple of very
to
quick things. This
Yes.
time lapse is about 5 hours long. And the way we know
Mhm.
this is at the start of the movie. If you click one more time, at the start of the movie, the Milky Way is nearly horizontal.
Mhm. Let's go back to the start. Wait, give me a sec. Oh, yes.
The Milky Way is nearly horizontal at the start, but it's not
Yes.
quite vertical at the end. In exactly 6 hours, it would go from horizontal to vertical.
Wonderful.
In another 6 hours, it would be horizontal but upside down, and in 24
Mhm.
hours, it would be back. So that's how we sort of know. As you said, this is a time lapse actually taken by one of my friends in California, but he took this, as you said, from a very dark side, from a game park in Kenya near the equator. So from Masai Mara.
Wonderful. Yes.
The
Yes,
other
I was
thing,
going to ask that. It
yeah.
looked like they had a nice view of the the southern sky.
Yeah,
So
exactly. The
it's
other
like
thing I
taken
was
from the
going to
equator.
say, Hero, about the Andromeda Galaxy, the best analogy I can think of is when someone throws a frisbee at you and you're about to catch the frisbee, it's both spinning and moving towards you, and that's how Andromeda is to us. It's
Wonderful. Very, very cool analogy. Yes. Yeah, that is very nice. So this is to connect with what Raja was saying here. This is like a view that we have of our galaxy because we are within it. Our solar system is only one of the dots that you can see in this beautiful image. It's just another one of these dots. It's just that we happen to be orbiting around it. But we can see our whole city, like cosmic city, that is the Milky Way galaxy that hosts a bunch of smaller neighborhoods. And this is kind of the view that you would have. If you live in a very big city, for example, and you try to look around it, you will need to move a couple of blocks to really see the extent of your city from this perspective that you're in. And that's kind of the situation that we are in. To really, really see the galaxy from a much wider and much uh, like more normal perspective as to what you see when you draw a galaxy and you draw a little pinwheel that is very, very pretty. You would have to fly for millions of years at the speed of light to really have that view that we get in the drawings. But we'll get to see those animations. So here we have another one that is an interesting perspective. You saw Raja was mentioning that was a bit less than 5 hours of the Earth's rotation taking into effect. But it looks like the sky is rotating around us. But we know now that that is really not the case. If we play this other kind of trippy animation or this other time lapse, what do you think of this? So look how the galactic plane stands still as the horizon is rising. The west horizon is rising up, covering the stars that we were seeing earlier. So that is a very interesting effect, and it's a very interesting way to see it. If you mount a camera and you try to really set the position of a star as fixed, you will notice that what's actually moving is the Earth, and that's something that we tend to lose track of, or like to really forget, because we are submerged in that perspective of living on top of a spinning spherical planet. So that is a very interesting thing to keep in mind. And we see that the galaxy is definitely a thing that is present there, and that all these stars are like probably following more complicated movements around that galaxy and not around the Earth. I don't know if you want to add something to that, Raja, or if we can move to the next one. So yeah, so this is an artist's impression of the Milky Way that I was mentioning earlier. We don't see this because we are embedded within the plane of the galaxy amongst hundreds of thousands of other stars. So our sun, not to scale here, would kind of be located in this position with respect to the center, uh, about 25,000 light years away from that core. But the thing is that we would have to travel at sci-fi like speeds to really have this kind of aerial view of our whole galaxy. It really, really is a huge, huge city that we live in our cosmic neighborhood. So that's pretty interesting. As Raja was mentioning, we are getting a frisbee thrown at us. So we are part of the conglomerate of all the stars that conform or like compose the Milky Way. But from very far away, we see another conglomerate of stars that is traveling towards us, and we know this thanks to catalogs like the one that we were analyzing just earlier. We see that this galaxy, the Andromeda galaxy, is flying towards us because when we analyze the spectra of many of its stars, they are blue shifted. They are shifted towards the negative velocities range, which means that they are approaching us. And it's on its way. I don't remember off the top of my head the exact amount of time that it will take for the collision properly happened? Do you happen to have it in mind, Raja?
About 5 billion years.
Yeah.
But there was a recent paper actually that came out from Till Sawala. I'll put the name in the chat. Till is the lead author of this paper, and I think if I think I have the first name correct. Um, Till is the lead author, but Alice Deason, who is a former postdoc of ours at UC Santa Cruz, she's on the paper. She's a faculty member at Durham now. This paper is about the probability of escaping a collision. That is, what is the chance that Andromeda will fly by as opposed to collide? And they claim that the probability is close to 50-50, and what is new about their
Oh, wow.
simulation is they put in realistic masses for not just for Andromeda and the Milky Way, which is what people have done in the past, but they've also included realistic masses for M33 and the Large Magellanic Cloud, because they also perturb the system. And so it's not a given that there will be a full-blown collision. There is a
Yeah.
finite probability of a flyby.
Yeah,
The
there
other,
definitely will be a dance. There's a dance that is
there will
starting
be.
between the two.
Andromeda will be much bigger in the future, will look much bigger to us in the future. That's a given because it is moving towards us. There's one other minor thing I wanted to mention, that is going back a little over 100 years ago. It's 2025 now, but if we go back to the early 1900s, there was a very important debate between Curtis and Shapley, two well-known astronomers of that time. And the debate was about the nature of these things that look like nebulae in the distance. Shapley said that our Milky Way is huge, it's very, very big, and all these nebulae are inside the Milky Way. All of them are inside the Milky Way. And Curtis said, no, our Milky Way is not very big, or our Milky Way is, is whatever size it is, but these nebulae are very far away, and they're as big as our Milky Way. They're not inside our Milky Way. They're comparable to the Milky Way. Turns out Curtis was mostly correct. He won the debate, but we now know that our Milky Way halo is so big that there are small galaxies orbiting within it. So there's a small element of truth to Shapley's view, but mostly Curtis is correct. I just wanted to add that.
Wonderful. Yes, that is from my journey starting to get acquainted with astrophysics research is definitely a breaking point, or like a very important inflection point in the way we think of our universe and the way that astronomers study the universe. So it's a very cool thing to mention, I think. So yeah,
Here I'm going to mention one other thing.
Go ahead, please.
This image of Andromeda should be flipped 180 degrees. The galaxy that's immediately above Andromeda should be immediately below it. It should be, not that one, but the one immediately above the center of Andromeda. That should, M32, if you point just above the disk, right above that one, that should be due south of the galaxy. So it should be a 180-degree rotation.
Wonderful, wonderful. Thanks for mentioning that. Yes, it has the two companions that then even in the maps you see.
Yeah, you can see the two companions, and the one that's further away from Andromeda's center should be to the upper right.
Oh, cool. Okay.
So
yeah, if you want to locate Andromeda in the night sky, if you have a clear night sky, you can look for the constellation of Andromeda. It's tied to the big rectangular shape of Pegasus. And if you have a clear enough sky, if you have a dark environment around you, you'll see, I like to think of it like as a small grain of rice that pops up into the distance. It's kind of faint, so you really have to look at it kind of with the side of your eye. Like you have to really look to the sides of it, and you can kind of start to make it appear. Because yeah, it is very bright, but it's like a brightness that is dispersed among along a big area in the sky. So for our eyes, it's not very friendly to see it immediately. But for a good camera, a good telescope that can collect its light for a while, it pops up in this beautiful shape and with these beautiful arm features. But yeah, but it is a very, very cool and interesting object to observe. And it's you might correct me, but this is the furthest away object that we can see with our naked eye from Earth, right? It's a beautiful thing to really put to perspective.
That is correct. As far as I know, it's the most distant thing we can see with our naked eyes.
So yeah, so this is kind of the plot that we just built with the data set. As we were mentioning, we just used a bunch of stars, the information that we have from the spectra of many, many stars. And each dot that we see here is one of the stars of Andromeda, and they are color coded from the velocity that we see them moving with respect to our perspective on Earth. So this really shows the rotation that is going on in the galaxy. The image that Raja was painting on our heads of the rotating frisbee that is approaching us. You can really see that, yes, it is as a whole an average moving towards us. So the average velocity is clearly negative, but you can see that it spreads over a huge range that kind of suggests that one side is rotating away from us and the other one is rotating towards us, while the whole disk is pushing towards the Milky Way. So that is a very interesting result that we can keep confirming with the spectroscopic observations of Andromeda. So this is what we were discussing about a moment ago. We have a collision scenario for the encounter of these two massive galaxies. So you have Andromeda and the Milky Way. This image has been updated since, and like we're mentioning that maybe it's around 4 or 5 billion years. But then now with more recent results, as the one that Raja was mentioning, there is some other alternative scenarios that might be considerable that we should take into account, like a possible like kind of flyby, like they do a little dance, but then one of the galaxies escapes with a larger velocity. They will definitely start exchanging some material between the two galaxies. There are two halos. The larger component of each of the galaxies, if the galaxies has a huge dark matter halo involving them. They are already interacting. These two halos are already gravitationally, let's say, kind of touching each other and kind of letting each other know that they're there. So that's a pretty interesting beginning of the interaction, beginning of the cosmic dance that is going to happen involving Andromeda and the Milky Way, but also the Triangulum Galaxy. M33 is going to be around. We were mentioning also the Magellanic Clouds are going to be also being tumbled to one side and the other by the whole by the huge gravitational pull of the two massive galaxies that are going to be interacting. So I think here is a good spot to switch to notebook 5, if I'm not wrong. What do you think, Jamika? How are we doing on schedule? So we can make sure to check out the simulated disk activity.
Yes, that sounds
And then I
good.
guess we can look quickly the last two animations that we have in the slides, and then we can see notebook 6 with a Parajito. Does that work?
The project.
Yeah.
Yeah, that sounds good. We have about
no-
50 minutes left, 50 minutes.
And notebook 5 is very short.
Yes. So here now we're gonna try to simulate, like play around with a simulation that has been prepared with a different script that kind of tells the computer, okay, these are the physics with which a bunch of points that make a disk would work, and kind of gives the script the geometry that we are expecting to build with a bunch of points. That file, you should find it also in the folder of the programs. And you'll see that there is a .py file. It's different from the other ones because this format, IPyNB, is the notebook format. So this tells Python, okay, this is a notebook. This will have cells of code and text alternating with each other, where you can run a bunch of things bit by bit. But then also there is the .py files that if you keep programming in the future, you will surely encounter them. They are files that are that we would call scripts, that are a set of orders that you can run in a single go and that do specific tasks that you tell them to do. So it's pretty much similar to what we do in the notebooks, but instead of being just a bunch of cells, you can think of it as a single cell that does one single thing, and that you can call from other scripts from outside of it. So in this case, we have this fake disk kind of script or function that what we'll do is will generate this disk object that we can use to compare to what we're seeing in the data set. So we have a bunch of parameters defined here. This is more internal of the functioning of this specific script. If you're a bit more advanced into the programming, I would advise you to have a look at it, to try to test your programming abilities by checking it out. So yeah, I would invite that. Even sometimes, if you have already a script that someone else wrote that you want to know what it does, in my case, I use some of these AI language models to feed the script to it and ask it, okay, can you help me navigate what this is doing? And it's pretty useful sometimes to get a picture. Be careful when you use AI language models to code. Not try to avoid maybe telling it, oh, please write a code that does this. Do that, but make sure to check, because sometimes it can give wrong answers. It can be misusing functions. It can be combining different versions of Python, for example, in this case, that might not work. But definitely for analyzing a code that you know already works, but you just want to make sure that you understand how it's operating, you can use these kinds of models very reliably to comment, to tell you what's happening in every step. And I would suggest that when you're facing more complicated scripts that were written by a more experienced programmer. So yeah, let's get back to the
Yeah, basically.
Yeah.
Yeah. Basically, just treat Python as a language. Programming languages, much like human languages, are, in fact, languages, and you have to understand the language yourself. You can ask for help, but at the end of the day, you have to make sure that it makes logical sense. And exactly like human languages, the more you practice, the better you get at it. So yeah, that should be your philosophy if you are taking help from an LLM. Because remember, it can't think for itself. So you have to make sure that you are doing the thinking and using it as a tool. And always, check out what other human beings have written when you are trying to troubleshoot an issue. Yeah, over to you, Baron.
Wonderful. That's a lovely contribution. I think yes, it's a good. I think yeah, we shouldn't be completely close to the use of AI in coding. It's definitely super helpful. It has helped me a lot, but definitely I've had to take care and be very critical, because sometimes it really doesn't understand what it's doing. It's just like guessing what's more likely to be the correct word to put after the previous. So yeah, I think that's always a fair warning to give. Thank you. So yeah, so now if we start running the cells of this notebook number 5, we're switching to number 5, you'll see that we are importing the module of the script that is called fakedisk.py. We can import it just like, just with the name fakedisk, which is the name of the file. We don't need to add the .py extension. And we can import the good old libraries of matplotlib and numpy and start working with that to simulate the shape of our disk and play around with the geometry and the kinematics of the disk. We're going to define this this function that is going to be, we're going to see it in practice, but it's going to be given the simulation object that is going to come out of the fake disk script. And to like just so you are aware of what maybe we will be changing more, this is the range of velocities that we're going to be playing around with for the visualization. So make sure to be aware of those parameters when you're going to change them, and make sure here at the end to add the line plt.show, so it's going to be showing properly in your plots if you're running this in parallel with us. So I can run that. That defines a function. Remember that the beginning of this cell says def. That's defining a function, so it's not going to run anything. It's going to simply create this function object that then we're going to call upon some variables, and we're going to use it to visualize our disk. So time to create our disk. We're going to call the fake disk script. with some specific parameters that we can define as variables here. So we're going to have several things. We're going to have the scale length of the disk. That's going to give us an idea of how big the disk is going to be in its radial extent. We have the dispersion within the layer. That's going to give us some movement of the stars, like some component of movement of the stars, kind of direction up and down. Also, not only in the orbit around the center of the disk. It's going to also give the each individual star a specific velocity component in the other direction of the disk, of the movement of the disk. So that's important always to have, because that's going to impact the global velocity that we measure in the system. We can also set a specific inclination, so how tilted in one of the axes, like at least this one I think is in the axis of the line of sight, is going to be inclined our disk. And then we can also do the position angle, which is going to simply rotate it on the plane of the sky that we are seeing. Yes, Jamika, please.
Yes, thank you, Geronimo. I just want to point out to Raja and Aparjito, there is a question in the chat about whether or not there are other programming languages that are used for analysis and research in scenarios like this one, besides Python. Thank you.
Oh, wonderful. I can comment super quick on that, but I guess the guys can elaborate on the chat.
Sure, I can do
Nowadays-
that, Hero, if you want.
Please.
I'm just going to put the names of a few programming languages that I've seen
Wonderful,
people
thank
use.
you. Yes. My comment is going to be that Python is taking over since a few years back. There's some very robust things that maybe Python cannot handle that well. So maybe the ones that Raja is going to mention are more useful for that. So yeah, then okay, we can define each of these variables that are required for the fake disk function to run properly, to generate the proper disk, or like simulated disk object with the characteristics that we want. So here we're adding a couple of like size indicators, like the scale factor. The dispersion is gonna do that, like at that specific motion in the vertical direction, also in contrast with the radial rotation of the stars in the disk. You're gonna have then the setup, or like the configuration of the disk, that is going to be the inclination with respect to the line of sight, the position angle with respect to the plane of the sky, the rotation velocity, that is how fast the disk is going to be rotating around its axis. And you can also play around with the amount of points that you want to add. So you can, here we have 10,000. So this is the magic of programming. You can, all of these are probably calculations that a human can learn how to do. A human might be able to do one of these calculations and run the numbers on paper with a calculator or something. But then how long will it take to do that 100, 1,000, 10,000 times? Well, to Python, that just took less than a second. That was super quick. So we just generated with this set of parameters, we just generated a simulation object for our disk, and we can generate the plots of that one. Let's see how it looks. And we can see here that we have a disk that has been simulated to be rotating with a rotation velocity of 200 kilometers per second, and it's going to be inclined 77 degrees with respect to the visual. So you can see that in how inclined it looks like it looks, instead of like a circle, it looks more like an ellipse. But also we have the positioning angle that tilted that circle from being, or like that ellipse, from being just like kind of with the long axis like pointing towards the 0 direction, like towards the x-axis, but now we tilted it to a different position. So that's what just happened when we put here like 37.7. These angles are not there just randomly. I guess they kind of, if you look at it, it kind of looks similar to what we were seeing earlier of the way that we see the perspective on Andromeda, for example. So we have this one, we can rotate it the way that Raja was telling us, but it definitely looks like the definitely looks like the kind of shape of the disk that we are simulating here. So yeah, feel free to play around again in your own time with
And
changing these
Hero,
parameters. Yes, please.
one of the really difficult things I've found to explain is position angle, inclination and position angle. So here's how here's an explanation I've settled on. That if I'll share this with the group, if that makes any sense. It's particularly difficult to do this online. In person, here's what I would start with. When you think of any galaxy that's shaped like a disk, it's always easy to start first with let's say with a disk that's face on. That is, imagine holding a frisbee that's flat in front of you so you can read the label of the frisbee. Okay, let's start with that. Then the inclination angle decides how much to tilt it. If you tilt it by 90 degrees, now the disk is perfectly edge on. In fact, the inclination is defined as the angle between our eyes and the galaxy, so a line of sight, and the perpendicular to the disk. So when you start with the galaxy face on, that's an inclination of 0 because there's no angle, there's 0 angle between the perpendicular to the disk and our line of sight. And again, 90 is when it's perfectly edge on. So we start by inclining the disk. In Andromeda, the inclination angle is 77 degrees. But let's say we always do the inclination about a horizontal axis. It's like rotating the frisbee about a horizontal axis. From perfectly vertical, we rotate it by 90 degrees. And if you can see my hands in the video, it goes from perfectly face on to 77 degrees. Then we can rotate in the plane of the sky, and that rotation in the plane of the sky, actually, let's start by rotating not about the horizontal axis, but about the vertical axis. Okay, vertical axis. So then Andromeda would look like this at 77 degrees. Then we change the position angle by rotating that axis, the major axis of that ellipse, counterclockwise. And for Andromeda, the position angle is plus 37. Nearly 45 plus 37, and that gives you the orientation that you were showing earlier. So again, start with a face-on disk, tilt it about a vertical axis, and then rotate the major axis in the plane of the sky counterclockwise. That gives you the position angle. That second angle is the position angle. I just thought I'd share that because I over the years, I found this very difficult to explain.
It is super illustrative. That really made sense. It really makes me even grasp it better also. So that's great. So yeah, feel free to play around with the different parameters. Play around to also grasp that idea that Raja was mentioning. Please, Aparajito, yes.
So sorry, I wasn't paying attention near the end. So have you I think it would be great to compare the actual data that we have in some of the slides with the disk here, because this is the simulated disk. This is the whole disk. And if you look at that little section of the data, it would be useful to compare the two pictures and just note the coordinates there to figure out exactly which part of the galaxy we're looking at.
Very cool. Yes.
The one drawback of the simulation it's a spinning frisbee, but it's static. It's not moving towards us in the simulation, at least. So you'll notice the center is at 0 velocity. It has a color of about green. That's the one way in which the simulation is not realistic. It doesn't have the translation motion. It only has rotation in it. But one really cool thing about the simulation is if you make the dispersion comparable to the rotation speed, you can no longer see the rotation pattern in the galaxy. And it's only when you make the dispersion much less. What is the dispersion and rotation speeds here for this particular simulation?
In this case, we put 100 in the dispersion.
100 for the dispersion and 200, right?
200.
So if you make the dispersion 200, for example, if you make them comparable, you'll see it'll be very hard to see the rotation.
Yes, it gets very...
And if you make it 300, you can no longer see the rotation.
Raja, chi, and eta are measured with respect to the center of M31?
Exactly. Those are projected
Yeah.
distances with respect to the center. Chi is along east-west. And you'll notice that chi is a reversed axis. It increases from right to left because east increases from right to left. And eta is from south to north. It increases from bottom to top. One thing you could try that is very beautiful is if you make the dispersion very small, like 10, and if you increase the number of data points a little bit, maybe by a factor of 10. And
You said dispersion 0, right?
not 0, that will blow up, but just small number like 10.
Okay.
Then you really see the beautiful rotation of the galaxy. So this was the last map. See, you see
Yes.
the beautiful rotation of the galaxy.
Wonderful. That looks really, really cool. Yeah, as you increase the amount of points, you really smooth out the scatter of all the stars that you're simulating to have here. That is really, really cool. So here, oh yeah, I ran this one with that amount of points. So apparently it's having trouble because it's many operations. But we can see what happens. I was talking about this yesterday, so some guys were like a bit scared that some cell was not running. They were having like the asterisk not going away. So yeah, sometimes if you ask for a very big computation and maybe your computer cannot handle it, or like it's truly very big and many computers cannot handle it, you might have to wait for a little bit, or you can cancel you can interrupt the kernel by clicking here in kernel and then interrupting it, and it will tell you, hey, I was doing these computations, but you did a manual interrupt. So I'm gonna just to make it easier for the computer, I'll set it back.
That's a good move. It's only for making the map that I suggested 10 times more, otherwise you're doing exactly the right thing.
Yeah, it gets what people call computationally expensive, because you would need a more powerful computers to keep calculating that high. So yeah, so here we're using a smoothing circle for this section. You can explore also a little bit playing around with this setup, with the different parameters, trying to make it match with the data set that we're working with. But yeah, and you can do square cutout. Let's see, and we can kind of zoom in into the central part of the circle and start to really compare with the data that we are observing from notebook 4, because you see what Aparjito was mentioning is that we have here, like, we're around the 10-15 kiloparsecs of the center of the data set, and we can see here that with that last cutout, we went very close in, so we can play around with changing some of the parameters to get closer to that. So yeah, that is a thing to play around with. But I think we're slightly short on time, so we can look at it maybe and read some of the questions that you have that you have here, and we can take the discussion to the Slack, so we don't get over the time very much today, because yeah, there's a couple of things that we can discuss, but to finish up maybe the discussion in the slides, you see that we have something interesting, and is that there is an effect when you have the rotation of a system that is not a rigid system. So it's Raja was mentioning the frisbee, but this gets a little bit more complicated than just a frisbee flying towards us, because it's a frisbee kind of made of particles that interact more weakly with each other than the plastic particles of a frisbee. Because a frisbee is a rigid object that is rotating all of it at the same rate. In this case, we have what we call differential rotation, which is more similar to what happens when you have, for example, cocoa on a glass of hot milk, and you start spinning it. The rotation on the outside is not necessarily going at the same rate as the rotation on the inside. This happens with generally with fluids, generally when you see the rotation of the sun, when you see how the atmosphere of planets like the Earth or Venus moves during the day, we see the effect of differential rotation, and then it definitely happens in galaxies composed of small particles compared to the size of the galaxy that are the stars and the parcels of gas that are traveling around the galaxy. So definitely we see the differential rotation when we look at the rates of the speeds that we measure along the disk. So it's
And
not
Hero, I really like your
that smooth.
cocoa and milk analogy, or
Yes.
milk and coffee analogy, because if you actually spin your milk before you pour in chocolate or cocoa into it, or spin your coffee before you pour in milk, you actually do get the spiral pattern, because exactly as you said, what is differential about the rotation are the periods. The central
Mm-hmm.
parts have a shorter rotation period than the outer parts. And the moment you have that, you get this kind of spiral pattern.
Yes. Wonderful. Yeah, yeah. I really like it. I think about galaxies every time that I make some coffee, like some latte coffee. It's fun. Uh, so yeah, so then we get to the topic of galaxy rotation curves, and that's how we finish these slides before moving quickly to notebook 6. We can have a look at this more closely. I was mentioning earlier that there is a thing called the halo, or like the dark matter halo of the galaxies, that in the case of Andromeda and the Milky Way, these components of each galaxy are already interacting with each other, um, and are kind of the way that we know that the collision is, or like at least the flyby is happening. So one of the two, but the interaction is definitely happening. Uh, so we see when you measure the velocity, the individual velocities of the stars that make up a galaxy, you observe that as you go outside of the center, like as you go far away from the center of the disk, um, the first you see a big bump, a big increase in the orbital velocity of the stars at each different radius. So you can start to think of this like as if you go from the center here, 0, and you start going to bigger radii as you go towards the edge of the galaxy, you will have first a bump where the stars will start to move very, very quickly from the previous orbit to the next. And then at some point it kind of plateaus and then starts to fall more slowly. And that's what is being shown here. You see that it goes up very quickly and then it starts to go to plateau and even decrease, but very, very slowly. The first time that this was observed, this made a lot of people scratch their heads because it's really not what is expected. When you think of this just the sole disk distribution of matter, and you apply what we know about Newtonian gravity to it, you would expect a curve more like this one. So you expect the bump, but then um, you expect the velocities of the stars as you go out to decrease more dramatically, to decrease more quickly. Um, so this suggested to people that there has to be some matter that is there in all galaxies, because this was an effect that started to show up in every galaxy that people were observing. There has to be more to it than just the matter that you see. There has to be some form of dark matter that is not easy to catch. It's not emitting emitting the light. So there is something that the galaxy researchers talk about a lot, that is the light to mass ratio. So the light to mass ratio was not really what they expected. There had to be more mass to explain the dynamics of galaxies. So some people start to do models of, okay, let's separate what a galaxy is into separate sections or components. And we say, okay, there's the disk, where a lot of the stars and the star formation is happening, and that's going to contribute this amount to the rotation curve. And then there's the bulge that also is like the more central part, that is like the more spherical distribution you see around the core of the galaxy. So kind of you have the disk that is this whole distribution, and you have the bulge inside that's more spherical. And you will have these two contributions, but still that is not enough. So that's when some researchers started to suggest that there had to be a halo of dark matter that extends way beyond the reach of the disk, and that really explains where the speed of the of the orbits of the stars is coming from. And that's how nowadays we fit the shape of the velocity curves or the rotation curves that we find nowadays. I don't know if you want to add something to that, Raja. It's
I
definitely
just
not my
wanted to
topic. I've done
say,
this a couple of times, but
I
not
just
very
wanted to
familiar.
throw out a name there, which is Vera Rubin, was the
Yes,
person who
completely.
made these measurements. And I was very fortunate that when I was in grad school, my second research project, which started at the end of 1985 or beginning of 1986, was on rotation curves of galaxies, measuring the neutral hydrogen, the H1
Yeah.
rotation curves of galaxies, spiral galaxies in the Virgo cluster. While I was just starting this project, Vera had already been working on rotation curves of galaxies. She is considered the discoverer of dark matter in galaxies.
Dark matter, yeah.
So Vera was actually measuring rotation curves of Virgo galaxies also using H alpha. I was using H1, but she became an informal mentor to me. And so I feel very connected to this work through, early part of my academic journey as an academic researcher.
That's wonderful. Yeah, that is lovely. Vera Rubin is an icon in astrophysics nowadays. It's a what you call someone opening trails for the future of astrophysics with her work. And it's wonderful that nowadays we have almost underway the Vera C. Rubin Observatory about to open its dome to start getting some starlight in Chile. So that's wonderful, and to keep revolutionizing astrophysics. So that is a lovely addition to have. So yeah, I think that's it on this side of the presentation. We can, if you're ready, Aparajita, we can move to notebook 6.
Yes, and we have just about 25 minutes left.
Wonderful.
Okay. Hope you guys can hear me loud and clear.
Yes.
Let me share my Chrome window. Okay. So we are in the final part of the Python and Research tutorial. 2025 week 2. Let's turn on some line numbers. Okay.
Aparajito, one of the things I love about Notebook 6 is it has the most difficult line of Python coding in all of PR. It's a very innocuous and simple looking line, but it's its simplicity. It's the combination of its apparent simplicity with its immense depth of meaning that makes that line so complicated. I'm giving it away, but you'll get to that line. I'm just going to step away for a few minutes, and I'll keep my sound and video off while I do that.
So let's get started. And we have imported the necessary stuff as we have been doing. Let's see if we can find the line that Raja just mentioned. So we have defined an user-defined function called showMap. It takes 5 parameters, chi and eta, which are the relative coordinates. These are the relative distances, vertical and horizontal, with respect to the center of the Andromeda galaxy. These are projected distances at the distance of the Andromeda galaxy. So it takes chi and eta, the 2 relative coordinates. It takes a quantity, and it takes a label, and it takes a file name. So essentially, it just plots a figure with chi and eta on the 2 axes, and it essentially just plots the quantity as a color map, and it saves the figure using the file name that you provided. Okay, so let me just add a little BLD.show right here, so that I don't have to add it on every cell. Let's think ahead. And then we do, and then we have to figure out exactly what quantity we want to plot in these figures. You might have guessed by now, based on what Geronimo described in so much detail with the simulated disk. We are literally just going to do the exact same thing but with real data and see if the results line up with what the simulations showed us. So we are going to plot the dispersion, the velocity dispersion. And for that, we define this user-defined function called getDispersion with the parameters x, z or z, v, and circle size. So what does it do? It just takes two coordinates, essentially one horizontal and one vertical. We are dealing with a three-dimensional reference frame. That's why we are using z or z. And then we take a velocity array, a set of velocities that goes along with the set of coordinates. And then we take a circle size. So we kind of have to define the radius in which we calculate the dispersion, right? Because we can't just calculate the dispersion for the entire map. That would completely throw things off. And we can't, and we have to make sure that we get a nice little sample that defines that region, but it is not too big so that, it covers other regions, contaminates the data, makes it pointless. So we have set a default circle size of, 300 arcseconds. So this function loops over the length of the length of these arrays, length of x, c, and v, which are all supposed to be of the same length. And it basically defines an empty array before that, composed of only zeros. That is, once again, the same length as the input arrays. And then it picks a single element from each of these arrays. First, it takes one element, and then it calculates the distance to every single star from this point. Okay, so every single other point from this point, and then it picks out the stars that are closest to this star, or specifically closer than the radius defined by the circle size. Okay, so you loop over the entire data set, you take every single point, and then you calculate the distance, the direct distance, perpendicular to the line of sight, of every single other point to that selected point. And then you only pick the sample of points that fall within the circle radius defined by the user. And you keep those points, you calculate the dispersion, the velocity dispersion, and then you reject everything else. So that's how we pick a sample and we reject the other points. And we do this for every single point, okay? So how do we calculate the distance? Now, this is where these two lines essentially is where there's a lot of simplicity, complexity. I'm going to paste something, or okay, rather let's just make this from scratch instead of pasting it, because I have the answer, but I can just do that. So we have learned that we can both operate between two arrays of the same size, but it would be element-wise operation, or we can do an operation between an array and a scale, all right? So that would operate the single scalar to every single item, every single element in that array, all right? So we are going to take advantage of both of these features of NumPy arrays. Let's calculate the x distances to every single point from this point xi. Our point is xi, right? And the distance to every single point would be x minus xi, right? We have given a neat little name to xi, so we're going to simplify this, make it easier to read using this x, okay? This is the x distance to every single point from our selected point. And obviously you will see that this is sign dependent. So we're just going to square this, and we're going to do the exact same thing with the y. You'll see that this looks very familiar because this is exactly what we did with the norm function in notebook number 1. So this formula should be very familiar to you, except we are doing this with arrays. We are doing this with real data, right? And then obviously we want the absolute distance. We don't want the sum of the squares. So what we do, we take the square root. Okay. So we are doing exactly what we did with the norm function. Let's pull that up. And we are adding the layers of complexity to that very simple formula. Because we are able to use NumPy arrays. Let's see. By the way, if anybody has any questions at this point, please ask, because like Raja says, that is the most complex line of code. It looks deceptively simple, obviously. Here you go. As you can see, exact same formula, x squared plus y squared, take the sum and take the square root of that. That's exactly what we do, except this is a vector, this is an array, this is a scalar, this is one single float, this is one single data point. And if we take the difference of this, we will get an array. We're taking the square of an array and the square of another similar array. We are then adding those two squared arrays to get another third array. And then we are taking the square root of that third array to get a fourth array. And we're calling it distance or dist. If anybody has any questions at this point, feel free to ask.
We have a question over in the Slack channel,
Okay.
which I think maybe Raja and or Geronimo will get to, but no questions here in the Zoom chat of Rajita. Thank you.
So since we have calculated the distances, now we can just pick the distances that is smaller than the circle size. How do you do that? We already know a Boolean array, right? So we're just going to say distance shorter than circle size. By the way, I just hit tab there. You can just, hit tab and it shows you a quick little list of the variables available in the namespace. Okay. And finally, we have to calculate the dispersion. And for that, we have, I think the function is std. We are taking the standard deviation. This function will take the standard deviation. It will give you the standard deviation of whatever you put inside, and it has to be an array. So we are going to only take the velocities of the points selected by that Boolean array, which is key. Okay, voila. That is the entire function. That's the magic of these 3 lines. Okay. And now let's put it to some good use. And we're going to load the data of chi, eta, and the velocities from the MS catalog, the main sequence stars that we created with notebook number 3. Remember, if you have not run it yet, you will not be able to do this step with notebook number 6. And we have selected keep. We have done a little thing here. This block of code, I won't get into it. As you can see, it just says it is meant to fix a bug in the data set. We kind of have to do these little patches sometimes. This is very realistic. If you're working with real data, you'll need to do this kind of patches. And we're just going to make a map of the main sequence stars, specifically their velocity dispersion within our data set, and map it onto the sky. So let's run that. And you can see it looks really beautiful. There's not all the stars are present. You have seen all the stars in Hieronymus' notebook, in notebook number 5. It was a much dense clustering of points. You can see only a subset of those points were selected, and you can see that they are, more or less evenly distributed in the data set. And you can see that velocity dispersion is relatively low in these regions. There's a bit of high dispersion right here in the corner, and there's a big area of high dispersion near the center. As you can see, this is the center right here. As you approach the center, things get more chaotic because that's what the AGNs are. We're going to copy this and paste it here, or I'm just going to rather save some time and copy it over from a different notebook that I already have. So this is the data for the AGB stars. This is the map of the AGB stars, and you can see the velocity dispersion is actually a bit higher. So in fact, there is value in this research, right? The velocity dispersion for the different types of stars is not identical. It varies. It varies with the star's age. Velocity dispersion is a value that varies with the star's age. And the longer a star has been around, the more collisions of the galaxy it must have experienced. So it carries that history with it. And finally, the RGB stars, which you can see also has a very high dispersion, even higher than the AGB dispersions. Finally, let's plot some histograms. I'll also copy over this code. I think this might take some tweaking to work. Maybe not. Yeah. Okay, let's troubleshoot that. I'm just going to take this error code and paste it onto Google. As you can see, Stack Overflow always has an answer.
Yes, 95%
And
of
the
problems you'll have
yes.
when you learn to
If
code.
you and yeah, if you can't find it, chances are that you're not phrasing it correctly. And if you really can't find it, congratulations, you are an advanced programmer. You have run into something that nobody else has ever run into before. And I have a couple of times. It's very rare, trust me. Pins. We can just maybe remove that part.
I guess what it's telling you, yeah, instead of norm, you should use density equal true. I think that's I think that's what it's telling you to do.
Yeah. Let's see, does it work though? Let's first remove the norm bits. Okay, that kind of works. Yeah. The labels are a bit messed up, and do that again. Yeah, perfect. So the labels are a little bit messed up, but you can probably tell. The red is the main sequence stars. Sorry, the red is the RGB, the blue is the main sequence, and the green is the AGB. Just reason we had marked in the final, in the final figure in notebook number 3. As you can see, the RGB stars have the highest dispersion. You can see that the peak is furthest to the right. The AGB stars are somewhere in the middle, and the main sequence stars in blue are somewhere to the left, which is what you can see in the velocity dispersion maps. That is all, Jamika.
Yes, I have a quick question. There are two questions that I've posted down in the chat. And the first one requests that you scroll back up to the cell with the standard deviation NP.std line.
Yes.
And that second question from Tejo, I believe Raja or Geronimo can answer in the chat. Thank you.
Yes, I can answer that one.
Okay, so this is the line np.std v keep. So we have figured out how to calculate the distances using the power of numpy and the formula that we learned with the very first function that we defined in notebook number 1. We defined a Boolean array that we can use to help us select only the points that are closest to the selected point, to each selected point, okay? To take a little sample of the points closest in the neighborhood. And then once we have that Boolean array, we can just use it to pick the velocity values to create the standard deviation. Because we are taking velocity dispersion. That is what velocity dispersion is. It is the standard deviation of a list of velocities. So yeah,
Great,
this is the
you.
sample of velocities, and this is standard deviation.
Maybe sorry, Prajito, can you maybe show the whole function, that whole cell?
This one?
Yes, because I didn't catch the whole thing from the definition. But yeah, but it's because I don't have that version of the notebook, and maybe it could be useful to share with the guys following.
As for the very final cell, I used a little bit of deprecated code, but we fixed it quickly. And you can basically, I hope you can figure that out. Everyone can figure that out with a little bit of Googling. You have used enough of Matplotlib by now. You've created one-dimensional plots with notebook number 2. You've created two-dimensional plots with notebook number 3. And you've essentially created three-dimensional plots with notebook number 5, because you have 2 dimensions. And then you have a third dimension with the color map. And we repeat that in notebook number 6. So, at that point, you can figure out how to make a histogram. So yeah. If you can improve that code, please go ahead. Any final questions?
The question is, can you scroll down to the read data portion?
Sure.
That note?
This one? I think this is it, right? Yeah.
Yes.
So we are just, unpacking it. You will have this line of code in your notebook, in your incomplete notebook, and you'll be reading in the MS catalog for the main sequence stars that you created using notebook number 3. You'll be reading in the AGB catalog for the AGB stars that you created using notebook number 3. And you'll be reading in RGB catalog for the RGB stars that you created using notebook number 3. Remember to add this block of code for every single cell, because this does some debugging stuff. And the rest should be identical. Just, switch around the variable names a little bit. Rename the PNG so that you don't override the PNG. Yeah, that's it. I hope that answers the question.